Okay, 27 review. 500 draws are made at random with replacement from a box of numbered tickets. 276 are positive. Someone tells you that 50% of the tickets in the box show positive numbers. Do you believe it? Okay. Now, before I write anything down, let's think about this. What test are we going to run? A z-test. Is it a one sample z-test or is it a two sample z-test? One sample. Why? We we only have one sample and we're comparing it to an expected value. What does a two sample z-test do? It compares two samples to each other and we look at the difference. Okay? So we're not, well, I guess technically we're looking at the difference between the expected and the observed, but we only have one sample here. So we're going to assume that 50% is correct. And then we're going to test the percentage we calculate against 50%. So there's not a huge difference between a one sample Z and a two sample Z. They're pretty much the same thing. But in a one sample Z, you're testing against an assumed value, whereas a two sample Z, you're comparing two samples to each other. Okay, so we think that the box is 0.5, 0.5 ones and 0.5 zeros. Okay, but we ended up taking 500 draws, and we ended up with 276 ones. What's that as a percentage? 276 divided by 500 is 55.2%. Now, what's that? Well, and so you're getting to what we need to look at. Do we use the SD of the sample or the SD of the expectation? We always use the SD of the box when we can. The only time we don't is if we don't have one. Can I create an SD from the box? Yes, so we use it. Okay, you always use the SD of the box when you can find it. If you don't have it, then you use the SD of the sample. So the SD of the box is 0.5. Is the SD of the sample going to be very different? No, it's going to be 0.499, 55%. So it doesn't really matter, but when we have a box, we use that SD. Okay? So I need to find an SE. Which SE am I going to find? SEP. Do I need to do an SE plus or an SD plus? No, because we have 500 draws, and that's plenty to do a z-test as opposed to a t-test. Okay? So the SEP is going to be 0.5 divided by the square root of 500. So 0.5 divided by the square root of 500. And I get 2.2%. Now, do I need an SE difference? Right. So there's only one sample. So we don't need an SE difference. And an SE difference is basically the Pythagorean theorem version of both SEs. But we're only using one SE here because we have a one sample test. We're not comparing two samples to each other. We're comparing one sample to an expected value, or what we think is in the box. So we don't need to do an SE difference. Do you guys see how one and two samples go together? Okay, if you're doing two samples, then you get two SDs and two SEs, and you take those two SEs and you create an SE difference. But here there's only one sample, and we Right. This is the chapter 26 stuff that we did. Okay. So now I draw my normal curve. I put 50 in the middle, and I go up to 55.2. Then I find the z-score, which is going to be 55.2 minus 50, which is 5.2, and divide that by 2.2. 5.2 divided by 2.2, and I get a z-score of 2.36. Then I shade norm, but I know the answer is it's significant, so I would reject the null because it's over 1.64. Do we think it's highly significant? What did you get when you shade norm? So let's zoom recall. Oh, I'm sure you're right. I just want to get the p-value. So 2.36 to 5. And we get a p-value of 0.009. So this is highly significant. Okay. So that's good to know. 2.36 is kind of the breaking point of highly significant. Okay. So we reject the null, which said 50 is correct, and we say we do not believe that the box has 50% positive numbers. Okay. Have we said anything about what we think is in the box? Actually in there? No. We just don't think it's 50. We think it's more than 50. Okay. You could build a confidence interval to say we think it's between here and here, but that wasn't part of the problem. We just were testing if 50 was true. All right. Number 3. The Gallup poll asks residents how they would rate the honesty and ethical standards of people in different fields, very high, high, average, low, or very low. The percentage who rated clergy very high or high dropped from 60% in 2000 to 54% in 2005. This may have been due to scandals involving sex abuse, or it may have been chance variation. You may assume that in each year they did a simple random sample of 1,000 persons. Should you make a 1-sample z-test or a 2-sample z-test? 2. How come? 2 samples. So that 60%. Is 60% a parameter or a statistic? It's a statistic. How come? We didn't ask every priest, right? So going back to problem number 1, is the 50% a statistic or a parameter? In the first problem, 50% it was a parameter. We don't think it was the correct parameter, but we pretended that it was a parameter. So in number 3, we have 2 statistics. One is 60% and one is 54%. We don't know what the parameter is. It exists, but we didn't talk to everybody. There's just, oh, and we're not measuring priests, we're actually measuring just people, regular people. So we have 2 boxes. We make 1,000 draws in the first box, and we got 60% in our sample. We ask 1,000 people in the second box, and we get 54%. Are these independent? Does an answer in 2000 affect an answer in 2005? No. They might be the same people, but probably not. So we need to find the SD. The square root of 0.6 times 0.4, and the square root of 0.54 times 0.46. Does somebody have those written down? What are they? The SDs. 0.489 and okay. Now I take the square root of the sum of the squares and I get oh wait. Nope. Hold on a second. 0.498. So I divide by the square root of 1,000. That will give me the SEP 1.54% and 1. It's still they're the same. Okay. Now I take the square root of the sum of the squares. Excuse me. And what do I get for an SEP? SE difference. 2.17. Okay. Now what do I do? Z-score. 60 minus 54 is 6. We divide that by 2.17. 6 divided by 2.17. And I get 2.76, which we now know is highly significant because the last one was 2.36, and that was highly significant. So my p-value is less than 0, which means I reject the null, and I accept the alternative, and the alternative said the the 2000 was bigger than the 2005. So are we safe to say that public opinion went down? Yes. That is a statistically significant test. In fact, it's a statistically highly significant result. Okay. What was the next one? 5. One experiment involved 383. 1, 3, 7, 8, 9. Oh, 7. When convicts are released from prison, they have no money, and there is a high rate of recidivism. Recidivism. Do you guys know what that means? They return. So the recidivism rate means how many people that are released from prison make it back to prison again. And having a high recidivism rate is not good. Yeah, which means you have a lot of repeat offenders. The the idea behind jailing people is to give them time to change themselves and then let them go so they don't come back. Well, if a lot of people come back, then the system isn't working like it's supposed to. Would providing income support to ex-convicts during the first months after their release from prison reduce recidivism? So if we help them find jobs as they're leaving, will they come back less often than if we don't? The Department of Labor ran a randomized controlled experiment to find out. The experiment was done on a selected group of convicts being released from certain prisons in Texas and Georgia. Income support was provided. Like unemployment insurance, there was a control group which received no payment and 4 different treatment groups, differing slightly in the amounts paid. The exercise is on the results for Georgia and combines the 4 treatment groups into one. Assume the prisoners were randomized to treatment or control. 592 prisoners were assigned to the treatment group, and 48.3% of them rearrested within a year. So we are going to help these people earn money. And we are looking at 592 of them, and the recidivism rate was 48.3%. Isn't that shocking? Half of the people who left Georgia prisons that made money on their way out came back. That's pretty terrible, right? Okay. 154 were assigned to the control. So this is the no money group. 154, and their recidivism rate was 49.4%. Now, yeah, we would hope that there would be a big, huge difference, but there's not. You know, that's only 1.1%. Okay, so we have two samples. We have to do a two-sample test because both of these are samples, not parameters. So we need to take the square root of 0.483 times 0.517, and that's going to be 0.499, right? So we got. And then this one is the square root of 0.494 times 0.4, oh, 0.506. So this one is also 0.499 because they're both so close to 1/2. So when I divide this by the square root of 592, what do I get? Yeah, 2.05, and I'm going to divide this one by the square root of 154. What is it? Why is this second one so much bigger? We didn't take as many people in that group, which means we're less sure about how accurate 4.94% is. Okay? So now I take the sum of the squares and square root it, and I get an SE difference of 4.51. Now what? Z-score. So I'm going to take 49.4 minus 48.3, and I get 1.1, and I divide that by 4.51, and I get a z-score of 0.24, which means we accept the null, and we say the program didn't help, right? Did helping these people find jobs affect the recidivism rate? It doesn't look like it. Nope. That is not a significantly um, significant, it's not a statistically significant difference. Okay, B. In the first year after their release from prison, those assigned to the treatment group averaged 16.8 weeks of paid work. The SD was 15.9 weeks. For those, we're on B. For those assigned to the control group, the average was 24.3 weeks and the SD was 17.3 weeks. Did income support reduce the amount that the co-workers worked? Answer yes or no and explain briefly. Oh, so I guess they were just giving them money, not, I misunderstood. So in the original one, it wasn't giving them jobs, it was giving them different amounts of money. So that didn't help. Katie, you confused? Or are you talking about something else? Okay, so yeah, so I misinterpreted the first question. It wasn't job help, it was just money. Okay. So, we have 592 people, and they had 16.8 weeks of, on average, of paid work with an SD of 15.9. Wow. That's huge, right? The SD is almost as big as the average. So there's a very wide range. And for the 154 people, they averaged 24.3 hours of work and with an SD of 17.3. Yeah, they're both really, really big. Okay, so I'm going to divide this by the square root of 592. What did that equal? Did anybody make it this? 0. So less than 1%. So 0.653%. That seems off to me. The square root of 592. Oh, this is an average. Okay, sorry, I was trying to do percentage. So 0.653. Thanks, Colton. And what do you get when you divide this one by the square root of 154? So 1.39. Now what do I do? SE difference. So I square root the sum of the squares. It's going to be 2. Oh, I was way off. 1.53. Okay, now what? Z-score, so 24.3 minus 16.8. And I divide that by 1.53. And I get a Z-score of 4.9. Which means reject the null. This is highly significant. So what can we conclude from this? So did giving people money on their way out of prison stop them from coming back? No. Okay. Did giving people money on their way out of prison affect how much they worked afterwards? Yes, in a highly significant way. Okay, the people who were given money worked 16.8 hours on average per week, and the people who weren't given money worked 24.3 hours, and we ended up with a p-value that's essentially 0. So, bad idea. Now, helping people find jobs might have a much better impact both on recidivism and money earned. But just giving them money didn't appear to help as far as recidivism was concerned, but it did seem to hurt how many hours they worked. Okay, 7, 8. All right, number 8's long. Okay, so pull out your calculators. I'm going to need your help. My calculator's too slow. One experiment contrasted response to prediction request and to request-only treatments in order to answer 2 research questions. 1, can people predict how well they will behave? And 2, do their predictions influence their behavior? In the prediction request group, subjects were first asked to predict whether they would agree to do some volunteer work. Then they were requested to do the work. In the request-only group, the subjects were requested to do the work. They were not asked to make predictions beforehand. In parts A, B, and C, a 2-sample z-test may or may not be legitimate. If it is legitimate, make it. If it is not, why not? So do you understand what the test is saying? So both groups are going to be asked to work. Okay? They're both going to be asked to do some volunteer work. Okay? The control group is simply going to be asked to do the work. The treatment group will be asked, how much work will you do? and then they will be asked to work. So the researchers want to know if you ask somebody how much they're willing to do, and then you watch how much they're willing to do, is that group going to be any different than just asking people to work? Does that make sense? Okay. Um, A. 46 uh, residents of Bloomington, Indiana were chosen at random for the prediction request treatment. So this is the treatment group. They were called and asked to predict whether they would agree to spend 3 hours collecting for the American Cancer Society if contacted over the telephone with such a request. Okay, so they asked them, if somebody were to call and ask you to do this, would you do it for 3 hours? 22 out of 46 said they would. Another 46 residents of that town were chosen at random for the request-only treatment. They were requested to spend the 3 hours collecting for the American Cancer Society. Only 2 out of 46 agreed to do it. Can the difference between 22 and 4 out of 46 and 2 out of 46 be due to chance? What do you say about the research questions 1 and 2? Can we do this? This one should be an obvious no. Well, there's no test here. Okay, so this group here was asked, how many of you would say yes? 22 out of 46 said they would say yes. These people were asked to do it, and 2 out of 46 did it. Well, we're missing something, right? We don't have 2 samples. This is asking, would you do it? Would you say yes? This group, yeah, they're not being asked the same question. We're missing this number here, right? So what we need to do is have the Cancer Society call those people and see how many of them actually will do the work. We don't have 2 similar samples. One sample said, would you be willing to say yes? And then you're supposed to ask them later if they will do it or not. So these are not the same sample. There's nothing to do here. Okay, B. 3 days later, the prediction request group was called again, and requested to spend 3 hours collecting for the American Cancer Society. 14 out of 46 agreed to do so. Can we now look at the difference between 14 and 2? Yes, because now, right. Okay. Um, what do you say about the research questions 1 and 2? Can people predict how well they will behave? 20. Is there a difference between 22 and 14? So we would need to do a 2 sample z-test, right? We would do a 2 sample z-test here, because we want to know, are people good at making their own predictions, right? Now, I'm not going to bother to do it, but you could do a 2 sample z-test right here and compare 22 to 14. And then we'll either end up with an answer that says, yes, they're good at it, or no, they're not. Okay? Then the next question says, did doing this affect people's answers? What would we do there? We would compare these, and we would probably get a highly significant result. Okay? Now, I'm not going to bother to do it. You know how to do it. Okay? C, can the differences between 22 and 14 be due to chance? So that would, we just talked about that, right? Um, okay. And number 10, An investigator wants to show that firstborn children score higher on IQ tests than secondborns. Uh-oh, I'm a secondborn. He takes a simple random sample of 400 two-child families in a school district, both children being enrolled in elementary school. He gives these children the WISC vocabulary test described in exercise 7 with the following results. The 400 firstborns averaged 29 and their ST is 10. The 400 secondborns averaged 28 and their ST was 10. He makes a two-sample Z-test. So he gets the SE of the firstborn is 0.5, the SE for the secondborn is 0.5, the SE difference is 0.7. The difference between their average is 1, and 1 divided by the SE for difference is 1.4, which gives us a p-value of 8%. Comment briefly on the use of statistical tests. Well, it said that there was no difference. Okay. Does anyone have a problem with this test? Yes. So they found 400 families that had 2 kids. And they tested the oldest and they tested the youngest. Ru They're different ages, right? Yeah, that is not a good idea. Now, maybe you could do that with people over 20 or 30, right? But if you're asking a 5th grader and comparing them to a 2nd grader, that's just not going to work. You can't give them the same test. So even though we ended up and said, no, we don't think that the older kids are smarter than the younger kids, it might actually be true that the younger kids are smarter than the older kids because they did the same and they were younger. So even though the test appears to be correct, the method was wrong. All right, we're done. We got